Hello everyone. We want to talk about equations of planes, in particular scalar equations. So we have a plane, and on this plane we have a point p sub 0 with coordinates of x naught, y naught, z naught. It's the coordinates of a point given, and we have another arbitrarily selected point p with coordinates of x, y, z. So basically 2 points on the plane. And we consider a vector that is perpendicular to the plane, and that is vector n, and we assume that this vector has components of a, b, c. And it's needless to say that any vector that is perpendicular to the plane, it is also perpendicular to any vector and any line on that plane. So basically, we can say here that vector n is perpendicular to vector P0P. We can say that. And vector P0P can easily be found. So P0P, that would be x of P, which is x, minus x of P sub 0, which is x naught. And then y minus y naught, and z minus z naught. So this is basically the P0P vector, which is perpendicular to the normal vector of the plane. So when two vectors are perpendicular, we know that they have a dot product of 0. So this vector is on the plane. It's vector P0P. One end point is point P sub 0, which is given. The other point is any arbitrary point we have selected. So this is vector P0P that is on the plane, and this one is the normal vector of the plane. And when a vector is normal to the plane, it is perpendicular to any vector on that plane, obviously. So because the dot product is 0, we know that two perpendicular vectors have a dot product of 0. So I can write down here a comma b comma c, which is the coordinates of or components of vector n, dot this other vector we had, z minus z naught. This is equal to 0. I can say the dot product is 0. And then we can do the multiplication. A times x naught plus b times y minus y naught, c times z minus z naught equals 0. Okay. And then when we simplify, we get ax plus by plus cz minus, I open brackets, factor -1 out, a times x naught plus b times y naught plus c times z naught. Okay, so let's not forget that a, b, c are just numbers, right? Those are the components of the normal vector. And x naught, y naught, z naught are also coordinates of a point given on the plane. So that is also a number. X naught, y naught, z naught are numbers. So this whole combination here, a times x naught plus b times y naught plus c times z naught, this combination is a number end of the day. So this number, I'm going to call it negative d, okay? So we get ax plus by plus cz plus d equals 0. So this becomes the equation of the plane, and we call this scalar equation, okay? So scalar equation of a plane is in this form of ax plus by plus cz plus d equals 0. And ABC here are actually the components of the normal vector. So these coefficients of x, y, z, ABC, are actually the components of the normal vector of the plane. Okay, so having said that, deriving this scalar equation, besides what we have before, such as vector equation and parametric equations, we're going to do some questions here. This is a vector equation of a plane, all right? And we want to write the scalar equation of this same plane. So how can we do that? Um, First of all, we can select a point on this plane, and that point could be point A with coordinates of -1, 4, and 2. Okay, And then we can select the two direction vectors. I could call them a vector A. Components could be 4, -10, 2. Okay. And the other component is -9, 18, and 3. So these two are direction vectors of the plane, which means that they are two vectors that are on this plane, just like this, okay? Now, if I write the cross product of these two vectors, it will be a vector which is perpendicular to the plane, and that is how we get the normal vector of the plane. So right now, I'm going to say n equals vector A cross vector B. So 4, -10, and 2 cross. I have to make this a bit easier. Instead of a 4, -10, 2, we can just reduce these numbers, because any vector that is collinear with vector A and collinear with vector B can be taken into account as the direction vector of the plane. So why bother working with larger numbers? Now that these numbers are all even numbers divisible by 2, why shouldn't I just conveniently take 2, -5, and 1, and here I take -3, 6, and 1 by dividing those components by 3. -9 divided by 3 is -3. 18 divided by 3 is going to be 6, and 3 divided by 3 is 1. So instead of vector B, I picked an easier vector, which is collinear with vector B, and instead of vector A, I picked again an easier vector. So now that I want to do cross product of these two vectors, I don't need to deal with large numbers. Okay, I will just find the cross product of these two vectors with smaller numbers. It's easier to do the cross product. And if you do the cross product, you are going to get the result of -11, -5, -3, okay? And this becomes the normal vector of the plane, okay? And I don't explain how you do the cross product because I'm sure you know it. And now these are the ABC values basically. And we had a point on the line from before. Don't forget, point A lies on the plane, because if you select T and S both to be 0, then X, Y, Z will be -1, 4, and 2. So I'm going to write AX plus BY plus CZ plus D equals 0, from where I get -11x minus 5y minus 3z plus D equals 0. This is the equation, but the D value has to be found. How? We are going to plug in the coordinates of point A in this equation and claiming that left side should equal to right side because the point lies on the plane. Therefore, its coordinates must satisfy the equation of the plane. So we're going to end up with -11 times -1 minus 5 times 4. I plug in 4 for y, minus 3 times, instead of z, we plug in 2, and plus D equals 0. So from here, if you solve this equation, you will end up with, of course, a D value of -15, or positive 15. We got to see. So that's 11. That's -20. So 11 -20, that is going to be -9. -9 minus 6, that's -15. And you move it to the other side, it becomes positive 15. So D is 15. So when you do the substitution, and when you multiply both sides of the equation by -1, just to have the x coefficient positive, you end up with the equation of 11x plus 5y plus 3z minus 15 equals 0. So that becomes the scalar equation of that vector equation of the plane given earlier. There's another example here. It says, find the scalar equation of a plane containing 3 points ABC. So 3 points in the space, they identify a plane. We want to write the equation of that plane, in particular, scalar equation of that plane. So it's needless to say that using points A and B, we can write vector AB. So you know how to do that: x of b minus x of a, y of b minus y of a, all of that. So 774 is vector AB. And vector AC similarly can be found as 8, -3, and 3. So these are the two vectors AB and AC, let's say. Now, we are trying to find the vector that is perpendicular to both of these vectors, which is this vector. So how can you find this other vector? Well, by doing the cross product, right? So we are going to write the cross product of those two vectors, and we're going to claim that that is going to be the normal vector of the plane. So do the cross product, you get 33, 11, -77. Again, large numbers, all divisible by 11. Therefore, we're going to reduce this conveniently. Conveniently, you can reduce that to 3, 1, -7. So that will be your normal vector of the plane. And then again, you start with 3x plus y minus 7z plus d equals 0, substituting for ABC that we just found as 3, 1, -7, plus d equals 0. Now, we don't know d, but we have like 3 points on the plane. We can pick any of those 3 points we feel like it. So I select point A. I could have selected point B and C and plug in their coordinates in the equation, but we selected point A. So -3, -1, -2, -3, -1, -2, we sub in for x, y, z, and from that equation we solve for capital D. And when you find the value of D, you can substitute back in the equation above, and there you go. 3x plus y minus 7z minus 4 equals 0 is the scalar equation of this plane that contains the 3 points A, B, C. So that's just another example right there. We did another example, conversion from vector equation into scalar form. That was just a proof of the scalar equation. And now there's another example here. It says, write the equation of a plane that contains this line, which means that this line is lying on the plane and it's perpendicular to this other line. So the plane is supposed to be perpendicular to this other line. Now the thing is that this other line has this direction vector of 2, 3, 1, and that direction vector of that line can play the role of the normal vector of the plane, because the normal vector of the plane, which is perpendicular to the plane, happens to be parallel to this line, or the direction vector of the line. So this means that we can say that the normal vector of the plane is nothing but the direction vector of the line, which is perpendicular to the plane. So we're going to go 2, 3, 1. That's the normal vector. And so this means that 2x plus 3y plus 1z plus d equals 0, right? And we need a point on the plane, okay, to write the equation of the plane. And what point can we select? I would say we select a point on the line, which is also on the plane. And the point is 1, 2, 4 given right there. So I'm going to plug in 1, 2, 4 instead of x, y, z. And I'm going to solve this equation. 4 times 1 plus d equals 0. So that's 2, 6, and 2 is 8. 8 and 4, 12. So d would be -12. So that means that 2x plus 3y plus 1z minus 12 equals 0 is the equation, a scalar equation of this plane, which contains the given line with the given equation, and it's perpendicular to the given line with all this information. So this would be the equation, a scalar equation of the plane, all right, given the conditions. I hope with these examples you got hang of how to write the scalar equation of a plane, and of course it's never enough. You know, the more you practice, the more you're going to learn about these, and I think I'm going to give you more examples in future. Thank you for now.